G'day folks, this is Chris and I'm back for another Chem 1011, Chem 1051 video tutorial. And in this video tutorial we're going to be talking about using the Rydberg equation to determine emission spectra of one electron systems. So the Rydberg equation is actually a nice little piece of algebra that we can use to determine the frequency or the wavelength or the energy of a photon that is emitted or absorbed when an electron jumps between energy levels inside an atom. And it works for one electron systems. Now you might be thinking, what's a one electron system? I know a hydrogen atom has one electron. Well, yeah, most of the time we're talking about a hydrogen atom. The reality is this Rydberg equation, it doesn't work as soon as you're talking about a system which has more than one electron. So you will have talked about that in lectures, so I'm not going to say too much more about that. But you might think of it like this. You can see the picture on the right-hand side has some concentric circles. These are kind of representing the energy levels of an electron. As the n equals 1, n equals 2, 3, 4, 5. As the number goes up, you're talking about higher energy levels that electron is allowed to have inside the atom. Now, as an electron jumps from a higher energy level back to a lower energy level, it emits an electron. Now, for what it's worth, it's actually possible to go in the opposite direction, and you could be in the n equals 1 and absorb a photon, and that electron would be elevated to a higher energy level, n equals 2 or 3 or 4, and so on. Point is, this little piece of algebra can be used to determine the wavelength of that photon, that little packet of energy. Remember, a photon is a little packet of energy. Or photons can be related back to their wavelength and back to their frequency. Anyway, so in this case, this little piece of algebra helps us work out the wavelength of the photon. Now, you'll notice that in the formula I've got N1 and N2. You look in some textbooks and you'll see this as NF and NI, where it means N final and N initial. That's fine. I like to call it N1 and N2 because that way you can use this piece of algebra no matter whether it's emission or absorption. N1 is always the lower energy level and N2 is always the higher energy level, and that's all you ever need to remember. Nice and simple. So an example of how we might use this piece of algebra could be for a question like this. If an electron relaxes from the n equals 5 down to the n equals 3 energy level, what is the wavelength in nanometers of the emitted photon? Determine both the frequency of the photon and the change in energy for the electron. Whoa, so there you go. We've actually got 3 questions in one here, so let's do it one at a time. What is the wavelength of the emitted photon? So here's our Rydberg equation. If I plug in the Rydberg constant, so the Rydberg constant 1.097 times 10 to the power of 7, and I multiply that by subbing in those two n values, so you can see I've got the lower energy level appearing first. In this case it's NF, it's N final because that's where the electron finishes, and 5 is the initial energy level for the electron. Plug that in and you'll get an answer. It's a bit strange, meters to the -1. Now we know that wavelength should be meters. Oh, it's a length, right? So it should be meters, not meters to the -1. But if you notice on the left-hand side of this equation, it does talk about 1 over the wavelength. So in that regard, you shouldn't be surprised that it's meters to the -1 because the wavelength is the reciprocal. It's upside down. So use your calculator and the reciprocal button on your calculator to flip this number over, and you should get the wavelength is 1.28 times 10 to the -6 meters. All right, that's the first part of the question. Determine the frequency of the photon. So, converting between wavelength and frequency. We use the wave equation. We did this in the first video, or the 2 videos ago, I should say. And it's the frequency equals speed of light divided by the wavelength. Well, we just worked out the wavelength in the previous question. And yeah, I know the question told us to work it out in nanometers, but you can do the conversion. We've got the answer in meters, so plug that into the equation. Speed of light divided by the wavelength, 1.28 times 10 to the -6, and you'll get the frequency of that photon. There you go, we've done the second part of the question. Finally, once we've got the frequency, we can now use this little piece of algebra to determine the energy. So in this case, it's the change in energy for the electron, or it's the energy of the photon, if you like. So E equals Planck's constant multiplied by the frequency. Planck's constant, 6.63 times 10 to the minus 34 joules seconds, multiplied by the frequency we got in the previous part of the question, 2.34 times 10 to the power of 14 seconds to the minus 1, also known as hertz. Straight in the calculator, and you should get this value here, 1.55 times 10 to the minus 19 joules. Now, there's something slightly wrong with my answer here. Can anyone guess what it is? Hit the pause button now and see if you can guess what it is. And when you unpause, I'll tell you what I've done wrong. All right, you've unpaused. The question asks for the change in the energy of the electron. The energy of the electron has decreased. It's more stable. So the change in energy should be negative. So the answer should really be minus 1.55 times 10 to the minus 19 joules. All right, lots in that question. Hopefully you're able to get your head around it. I'll see you in the next video.